All right, last topic for this week is derivatives of the trigonometric functions. So what are their derivatives? Let's start with what the basic functions look like, sines and cosines, and then we'll go from there. So here is the sine function. Here is the cosine function. So remember, sine functions start out at 0, then they increase up to a maximum of 1, decrease to a minimum of -1, and then back and repeat over and over again. Cosine functions do the same thing, but instead of starting at 0, so instead of starting here, they start at the top at 1. Otherwise, it's the exact same shape of a function. It's just a difference in where they start. So the sine function and the cosine function are really just shifts of the same shape. Now, on the picture here, I've indicated where the derivatives of these functions would be equal to 0. So everywhere it goes from increasing to decreasing, the function would go through a 0 slope. So 0 slope here, 0 slope here, 0, 0, and so on. All right, so then let's think about what the pictures of these derivatives would look like. So here in the sine function, you're increasing, so you'd have a positive slope. So the derivative would be positive here. So positive. Derivative would be 0 at the top, and then it would be decreasing, so it would become negative. And so it's decreasing slope all the way here. Back to 0 slope. So it's, negative slope, not necessarily decreasing, but it's negative slope from here to here, then positive slope from here to here. So what does that mean for the derivative? It means the derivative is going to be positive, go through 0, negative, go through 0, positive, go through 0, again, negative, go through 0, positive, go through 0. So it's going to be a cyclical function just like the sine. But think about where it starts and what it does from there. So at x equals 0, we're kind of halfway between this 0 point of the derivative and this 0 point of the derivative, right? And the slope is positive throughout, right? So the derivative of sine is going to be 0 here and 0 here and positive in between, right? So it's going to be shaped something like this. Now from pi over 2 to 3 pi over 2, it has a negative slope. The derivative is going to be negative, and then it will return to 0 here. So it goes up to a peak, down through here, then it's going to go down and back up to 0. And if you think about what I just traced out, I just traced out the shape of a cosine function. And in fact, that's what we find out, is that the derivative of the sine is just the cosine function. The derivative of the sine is the cosine function. What about for cosine? Let's just quickly think about this one. What's happening around x equals 0? Well, it reaches 0 here. So maybe the derivative of the cosine is just the sine, right? It's 0 at 0, right? 0 slope here, so 0 derivative at 0. But then think about what's happening on either side. Here it's got to be a negative slope, so it has to be a negative derivative. And here it has a positive slope, so it's going to have a positive derivative. So it's going through 0, but it's positive on this side and negative on this side. So it's not quite the sine, it's minus the sine, right? It's this function, but if you flipped it, reflected it across the y-axis, it's negative over here, positive over here. Sorry, positive over here, negative over here. Said that backwards, I think. All right, so derivative of the sine is the cosine. Derivative of the cosine is actually minus the sine. All right, so if you had trouble following it as I was saying it, this picture is just meant to illustrate the sine function anyway a little bit more clearly. So we have the sine function is the solid line, right? Starts out at 0, goes up to 1. And then the cosine function is its derivative, right? And so you can see what its derivative is doing. At 0, the sine function has a slope of 1. So its derivative is exactly 1. Then as you move forward, the curve here has a positive slope. So the derivative continues to be positive, but it's bending over towards 0. So it's decreasing down to 0. Now the orange section of this curve, the slope is negative. So it's a negative all throughout here. And then it reaches 0 again at the minimum. And then it's increasing from that point forward, right? The slope is getting bigger and bigger and bigger until it gets back up to 1 at 2 pi, and then the cycle is just going to repeat. So hopefully now you're convinced that the derivative of the sine function is just the cosine function. All right. Sorry, my picture here is blocking some of this, but you'll see this on another slide anyway. Derivative of the sine is cosine. Derivative of the cosine is minus the sine. Now that we have these two trig functions taken care of, if you want to see the full proof of this, you can go through it in the textbook. They lay out exactly how you can prove that it's exactly equal to the cosine. But hopefully at this point you believe me that the derivative of sine is cosine, derivative of cosine is minus sine. Now that we establish that, we can find any trig function, because any trig function is made up of sines and cosines. So let's think through that. These are the other 4 trig functions that you may be familiar with: cosecant, secant, tangent, cotangent. They are all built from sines and cosines, and in fact they're quotients relating sines and cosines. So 1 over the sine gives you cosecant, and so on. The graph over here is just to remind you what these functions look like. But the important point is that these functions are built from sines and cosines. Once we know the derivatives of these, we can just use the quotient rule to figure it out. So I want to look at one example, and then if you're really curious, or it would actually be good practice to try it out on these other functions to see what their derivatives come out to be. Well, let's just take one example. Tangent, use the quotient rule. Tangent is sine over cosine. So we want the derivative of this tangent function, and the quotient rule says the derivative of the top function times the bottom function minus the derivative of the bottom function times the top function. So that's what I've written out here. And then in the denominator, you just square the denominator. So cosine becomes cosine squared. All right, so derivative of sine we've determined is cosine. So what we have here is just cosine times cosine, cosine squared. And then over here, derivative of cosine is minus the sine. So I've put in minus sine. And then we have a minus minus situation. So that will become a plus. And then sine times sine will be sine squared. So what do we have here? Cosine squared plus sine squared over cosine squared. And there are different ways to simplify this, but one nice identity that you can apply is that if you take a cosine squared plus a sine squared, you get exactly 1. And that is essentially from the Pythagorean theorem. Remember the sides of a right triangle. If it's a unit length hypotenuse, you have the sine side and the cosine side. And so cosine squared plus sine squared gives you the hypotenuse, which is 1. Okay, that's 1. In the bottom we have cosine squared. So we have 1 over cosine squared. Another way to write that would be the secant squared. Remember, 1 over cosine is secant, So 1 over cosine squared is secant squared. So that's it. The derivative of tangent is secant squared. And then on the next slide, I have all of the other ones listed just for ease of reference. They're obviously listed in the textbook as well. We have 6 different trig functions here that you can go to. Any trig function you might encounter will always be some type of combination of sines and cosines, so you could just start out with that. But sometimes it's handy to know, like, what is the derivative of the tangent, so you don't have to figure it out every time through some combination of product and quotient rules. But they're all listed here, and that's it for this week's new material. When we pick up next week, we will start using a really useful rule called the chain rule and thinking about implicit differentiation. Those 2 techniques will help us really unlock this subject and give us a lot of applications that we can use derivatives for.